Hi guys, so this is chapter 10 part 4. It's the last video that you're going to be responsible for, and I'm starting with section 10.6. So in the last video we talked about the valence bond theory, and we talked about how, at least qualitatively, the valence bond theory explains the stability of certain molecules and why they come together, and shows us why it is that carbon makes 4 bonds and not 2 bonds because of its electronic configuration. It's that hybridization process. However, there are certain things that the valence bond theory cannot explain. For example, if I was to show you this molecule right now, it's O2, it's a gas, a diatomic molecule. If you write out the electronic configuration of this particular molecule, you'd see that there's no unpaired electrons. We've learned that molecules or atoms come together to fill their octets. So obviously there should be no unpaired electrons, and should be a diamagnetic molecule. If you think about it, that would mean that every molecule that comes together should be diamagnetic. But that's not the case. And one example is shown here with O2. Experiments have shown that oxygen molecule has 2 unpaired electrons. And that finding suggests that there's a fundamental deficiency in the valence bond theory. And that's why we had to justify searching for a new theory that explains these anomalies. Magnetic and other properties of molecules are sometimes better explained by another quantum mechanical approach, which is called the molecular orbital theory. It's a theory that describes covalent bonds in terms of molecular orbitals, not atomic orbitals like the valence bond theory does. So real quickly, the picture here shows liquid oxygen being poured through the poles of a magnet. If O2 was indeed diamagnetic, it would not get stuck between the magnets. But if you notice, there is a bit of a gaseous accumulation between those poles, and that's the liquid oxygen that's being attracted to the magnet. That wouldn't happen if oxygen was indeed diamagnetic. Alright, so according to the molecular orbital theory, or MO theory, the overlap of a 1s orbital of 2 hydrogen atoms leads to the formation of 2 molecular orbitals. One that's called a bonding molecular orbital and one that's called an anti-bonding molecular orbital. A bonding molecular orbital has lower energy and greater stability. The anti-bonding molecular orbital has higher energy and lower stability from the atomic orbitals that it came from. As those names suggest, if you place electrons in these different orbitals, you will either have a stable covalent bond, or if you place them in the anti-bonding, you're gonna have an unstable bond. And this concept of bonding and anti-bonding come from the fact that you have to remember that electrons in orbitals behave like waves. An electron in a bonding molecular orbital, the density is greatest between the nuclei of the 2 bonding atoms, but in an anti-bonding orbital, the electron density is actually 0 between the nuclei. So it's very unstable. If you think about waves, they can have that same type of connection, right? So if you have a constructive interference in a wave, you can enhance the amplitude of that wave, and that's what I'm showing you right here. On the other hand, if you have a destructive interference, you can basically delete that wave. The formation of these bonding molecular orbitals correspond to either constructive or destructive interference, just like waves. So here I'm showing you a picture of what we just talked about. This is an energy level diagram of an H2 molecule. However many atomic orbitals you have, that's how many molecular orbitals you're going to have. So in an H2 molecule, you have 2 hydrogens, and each of them have a 1s orbital. So that's why you have these 2 1s orbitals right here. And since you have 2 atomic orbitals, that means that you're going to have 2 molecular orbitals, one in the sigma bonding and one in the sigma anti-bonding. And as you can see, the lower bonding molecular orbital has lower energy, greater stability. That means it has a constructive type interference. The electron density actually falls in between the 2 nuclei of those 2 atoms, making that electron density even larger, even more stable. If you were to put the electrons in the upper box, which is the anti-bonding orbital, that means that the it's a destructive type interference. So if you can notice the electron density here, there's a nodal plane. That means that the electron density is actually 0. You notice that H2 is a very stable molecule because it has both of its electrons in the sigma bonding orbital. There are no electrons in the anti-bonding orbital. You fill them up from low to high first. Okay, you never start from high to low, always from low to high. Those two go in the first box, the lower box. So that's the bonding molecular orbital of the 1s orbital. Alright, so in the previous slide, I used the hydrogen molecule to illustrate these energy level diagrams in the molecular orbital theory, but obviously there's more complex molecules. What I want you to understand is that the concept is applicable to any molecule you have. So for example, something that has a 2s orbital or a 3s orbital can be understood in terms of the molecular orbital energy diagram that I just showed you for the 1s. Let's do an example for a 2p orbital. The only thing different between a 1s and a p orbital is that p orbitals are now involving molecules that can actually have double and triple bonds. So you have two possible interactions that can be happening between two equivalent p orbitals. So for example, two 2p orbitals can approach each other end to end to produce a sigma bond and a sigma antibond. And remember, if you have a constructive interference, you're going to have that electron density mostly between the two nuclei of the two atoms that are coming together. You can also have a sigma antibond in the 2p orbital, and if that's the case, then you're going to have your electron density is going to be actually 0 because it's going to be very unstable. Alternatively, you can have the 2p orbitals overlapping sideways to generate a bonding and an anti-bonding pi molecular orbital, and that's I'm showing you in the bottom. Again, they can have a destructive or a constructive interference. A pi molecular orbital, remember the electron density is concentrated above and below a line that's joining the two nuclei of the bonding atoms. So again, when the p orbitals overlap end to end, a sigma bond and a sigma anti-molecular bond are being formed. When the p orbitals overlap side to side, a pi bond and a pi anti-bond molecular orbital are being formed. Remember, if you have a double bond in a molecule, that double bond is made up of a sigma and a pi, and if you have a triple bond, that triple bond is made up of a sigma bond and two pi bonds. So we assume that the 2px orbitals are taking part in the sigma molecular orbitals, and the 2py and 2pz orbitals are actually interacting to form only the pi molecular orbitals. So I want to show you how to do molecular orbital configurations before we go into more complex energy level diagrams. These MO configurations are exactly the same as electron configurations that we learned before. We're just doing them with these different symbols that you're learning now, the sigma and the pi. Before we go into molecular orbital configurations, I wanted to go over some really quick rules that you need to actually do them correctly. To understand the properties of molecules, we must know how electrons are distributed among the molecular orbitals. The procedure for determining the electron configuration of a molecule, it's exactly the same thing, we're just using different symbols. So step 1, the number of MO orbitals formed is always equal to the number of atomic orbitals that you have. You can't come up with new orbitals, so whatever you start with is whatever you have in your molecular orbital diagram. Number 2, the more stable the bonding MO, the less stable the corresponding anti-bonding MO. Number 3, the filling of MOs proceeds from low to high. I've said that already. Number 4, each MO can only accommodate up to 2 electrons. So it's just like the orbitals that we talked about when we were talking about atoms. Each little line can only hold 2 electrons, so each molecular orbital can only hold 2 electrons. Number 5, you got to use Hund rule when adding electrons to MOs of the same energy. So what does that mean? You do spin up, spin up, spin up, and then you come back and fill them spin down, spin down, spin down, just like we did before when we were doing atomic orbitals. And number 6, the number of electrons in the MOs is equal to the sum of all the electrons on the bonding atoms. With the help of molecular orbital diagrams and the bond order, which I'm showing you here, we can approximate the strength of a bond as well as evaluate the stabilities of a certain molecule. The bond order is a very simple equation. It's just 1/2 times the number of electrons in bonding MOs minus the number of electrons in anti-bonding MOs. So what I'm going to do is I'm going to show you 4 different molecules. We're going to do the bond order for all 4 of them and evaluate evaluate whether or not these molecules exist and which one is more stable than the other. The first example is H2+. This is their diatomic hydrogen ion. So each hydrogen normally comes with one electron, but since this is the ion, it doesn't have a total of 2 electrons in the molecule, it only has 1. We would put that first electron in the sigma 1s bonding molecular orbital. The second molecule is your regular diatomic hydrogen. It has total of 2 electrons. Each hydrogen comes with 1. So you fill those 2 electrons in the sigma bonding molecular orbital. Your next example is your helium ion, which of course has a total of 3 electrons. You've put the first 2 on the bottom, and that third one goes on the top, the sigma 1s anti-bonding molecular orbital. The fourth one is your regular diatomic helium. So let's go ahead and figure out what the bond orders are for each of these. The first one is the number of electrons in bonding molecular orbitals, that's 1, minus the number of electrons in the anti-bonding molecular orbital, that's 0. 1 minus 0 is 1, times 1/2 is 1/2. Let's do it for diatomic hydrogen. Number of electrons in bonding molecular orbitals, that's 2, minus the anti-bonding electrons, that's 0. 2 minus 0 is 2, times 1/2 is 1. If you do the same thing for He2+, you see that you'd get a half, and He2 would be 0. Note that the bond order can be a fraction, as you see here, 2 of them are 1/2. But if you have a bond order that is 0 or a negative number, that means that that molecule is highly unstable and it probably doesn't exist. What bond order really means is the number of full covalent bonds that that molecule possesses. So if you have something like a 0, that means that it really doesn't have any covalent bonds. So it's really, really unstable. If you have something that has a 1 or any other digit, that means that it has that many full covalent bonds. So hydrogen, diatomic hydrogen, has 1 full covalent bond, and it is very stable. We know it is. It exists in our atmosphere. If you have something like a fraction, that just means that it has half of a full covalent bond. So it's not as unstable as something that has 0 or negative, but it's not as stable as something that has a full covalent bond, like diatomic hydrogen. So here, if I was to predict which one is less stable, I would say it would be diatomic helium, and then I would say H2+, then right next to it I would put He2+, and finally the most stable one would be the diatomic hydrogen. Now I want to do a little bit more complicated molecular orbital diagrams. I want to try the example of diatomic carbon. The electronic configuration of carbon is 1s2, 2s2, 2p2. Each carbon has 6 electrons, so that means that a molecule of carbon would have a total of 12 electrons. We have to take care of each orbital independently. So we go through the 1s orbital, the 2s orbital, and the 2p orbital. On the bottom left, I'm showing you the 1s orbital. So each carbon has 2 electrons. So we put 2 electrons in one atom and 2 electrons in the other atom. We fill the first 2 in the sigma 1s, and we fill the last 2 in the sigma star 1s. That's a total of 4 electrons, 2 coming from each carbon. We do the exact same thing for the next orbital, which is the 2s orbital. Each carbon, again, has 2. So since you have 2 carbons, you're going to have a total of 4 electrons. We're done with the 1s and the 2s orbital, and we've accounted for a total of 8 electrons. To do the 2p orbitals, you have to remember that p orbitals are consisted of 2px, 2py, and 2pz. Each carbon has 2 electrons in the 2p orbital. So you put 1 in the 2px and the 2py of each atom. So that means that there's going to be a total of 4 electrons in the bottom 2 boxes. And that's what I've shown you right here. Now, I want you to note that in this molecule, the sigma 2px orbital is higher in energy than either the pi 2py or the pi 2pz orbital. All that means is that the electrons in the sigma 2px orbital are less stable than those in the 2py and the 2pz. And also remember, the sigma is the one that's involved in the sigma bonding. And the pi's are the ones that are involved in the pi bonding, the double bonds, above and below. And the sigma is the end to end. So it just happens to be that the double bond is a little bit more stable in this particular molecule. And this anomaly happens with the diatomic molecules of lithium, boron, carbon, and nitrogen. Everybody else after that is what you would expect. The sigma 2px is lower in energy, and then the pi 2py and pi 2pz would be above it. So we've accounted for a total of 12 electrons, and the molecular orbital configuration of C2 would be sigma 1s2 because there's 2 electrons in the sigma 1s orbital. Sigma star has 2 electrons, sigma 2s, 2 electrons, sigma star 2s, 2 electrons, pi 2py, there's 2 electrons there, and the pi 2pz, 2 electrons there. Alright, so this is all you're going to need to know for your final. I suggest that you study this. I hope you've had a great semester, and good luck.